In this talk, I will summarize our results on distributed optimization in wireless relay networks. The slides are longer, but I will keep the presentation short. In the first work, we designed transmit and relay side beamforming matrices distributively. In the second work, we tried to make this fully distributed, which I will explain.
Yes.
So our expected output is compared to centralized and distributed solutions. We want less complexity per processing unit, and centralized solutions have a backhaul problem because they need to know all channel state information, whereas
Yes.
Distributed solutions, they need local channel state information. So we believe distributed solutions are important because now we are in the era of massive scales. We have many different demands for we have many challenging demands and different demands. So we need myriads of network entities, massive MIMO nodes, and so on. So we think these things might indicate that the future networks might be more designed towards more distributed architecture. So this is just a bit off the topic. This is just for interest. Blockchain is distributed technology. It is not only about Bitcoin. It is about any digital asset. It is being argued that dynamic spectrum sharing can be done via blockchain in 6G for spectrum leasing. We are trying to finish a conference paper on leasing relays based on blockchain technology currently, and there's a huge research on decentralized internet to eliminate censorship and privacy, because the current system is more centralized. We trust, for instance, Google for our privacy. They will protect our privacy. They want to peek in our privacy.
So I see.
So we think it's quite important. This is the network model we worked on. I can say briefly, everything is multiple in this setup. We have multiple antennas at every node, and we have multiple nodes at every side, transmit, relay, and receiver side. We have also multiple stream transmission, more than one data per user pair. And we have, I can turn on the pointer. We have this direct channels between transmitter and receivers. It is a challenging problem to design relay beamforming vectors because we cannot write SANR exactly when we have direct links, but we approximated the SANR and we showed that we can still get better results compared to only transmitting, optimizing the transmitters, or compared to having no direct channels, although we have approximation at the relay side. So this is the centralized distributed and fully distributed illustrations. So in this is the transmitter side. These are the relays. So in the centralized solution, this is the time index, time t plus 1. For instance, we can stack the beamforming vectors use and f are transmit and relay beamforming matrices. We can stack them in a single matrix, and we can solve the staggered matrix as a centralized solution. And once the solution is obtained at the transmitter side, we switch to the receiver side. So relay side, there's a coupling in two directions. One, vectors are coupled at transmitter and also there's a coupling between transmitter and relay side because they need to weight each other. So in the literature, usually this is the most conventional scheme. The coupling is solved in one direction, and it's called distributed solution. So user I solves its beamforming vector independently from other streams, from other beamforming vectors. So coupling is eliminated at the transmitter side, same as at the relay side. But we have still coupling between transmit and relay side. They need to weight each other. I'm talking about, iterative algorithms.
Yes.
So in the fully distributed case, any node can update its beamforming vectors at any time. We can call the former to as synchronous communication, and the last one as asynchronous communication. So it is a fact that if the network is more asynchronous, the convergence is slower. We need more iterations.
Yes.
But here in the distributed solution, there is also a delay because relay side needs to wait the slowest at the transmitter side, because they can start optimization. So this is what we did in the first work, and in the last work we did fully distributed solution. So
and asynchronous then. Yes.
Yes.
So, yeah.
Basically, in the first work, we used conventional ADMM to have this distribution at each side, and then we use consensus ADMM to decouple between transmitter and relays. We basically copied the relay filters to transmitters and transmitter filters to relays to achieve this decoupling. I will get to this point soon. So this is some publications within the scope of our paper. Everything is multiple antenna, everything is multiple. So it's quite...
Where are these references listed? 1 through 11?
I can send you the presentation if you like, Professor. It's at the end of the presentation.
Yeah, okay, I see.
So as an objective, we chose the minimization of some power of transmitters and relays. And under the quality of service constraint, we chose SNR as a constraint. So our expected output is to obtain the same total power consumption as with centralized and distributed solutions, but with a lower complexity, lower message exchange load, and higher convergence rate when compared to other existing distributed solutions. So we use conventional and consensus ADMM. We propose to distribute the algorithm over transmit streams, not to the users. At the transmitters, we optimize stream beamforming vectors per stream. At the relay side, we optimize relay matrices, each relay. So it is per stream. We think per stream is important because especially after massive MIMO and millimeter wave communication, since they are together coexisting, multi-stream per user transmission is very important. Before it was okay to assume single stream, but now due to massive MIMO. Image and video transmission, we can multiplex different parts of the image, for instance, on different streams. For example, we can multiplex the features of the face on streams with higher SNR and background or shoulder features on streams with lower SNR. So if the channel is in a bad condition, if you lose the stream SNR with low SNR, it is okay. It is still distinguishable at the other side. It is also time saving. If the user downloads the main features first, maybe the user wants to move to the next page. Right now the technology is mainly a single stream. It's multiplexed on single stream, but in the future it's possible that multi-stream along with massive MIMO will be at all layers of communication systems will be existing. So we think multi-stream communication is important. So this is some fundamentals that I did the presentation earlier at South Taiwan University in South Taiwan. Yes. So here I'm trying to explain what is consensus ADMM, but that's the main idea. So in the first work, we first solved transmit side with conventional ADMM, and the relay side again with conventional ADMM. So then it becomes distributed. Maybe I can go through this page. As you see here, let's assume it's a single antenna transmitter nodes. So they have a single scalar complex symbol. and let's assume the objective function can be separated to k functions, but they are coupled over variables. So this x is the global variable. So as you know, just I wanted to visualize how we apply in the relay case. That's why I'm going through this. I know it is your expertise. So let's say in the first iteration, we copy this global variable to each transmitter. Then each transmitter can solve the problem based on its own perspective. So when the local solutions, now these are local solutions at each node, are obtained, they are sent to central node to be averaged, and then a global variable is obtained to be used at the next iteration. And in the end, when the iterations stop, all nodes achieve the same result because we have this constraint at every side. So we apply this principle. Basically, we copy the relay filters to transmitter, transmit filters to relay, to decouple between those sides. But to decouple at each side, we use conventional. This is our idea. Since in the first work we use a conventional ADMM, and everything is multiple antenna, it is easier to make cross-parameter analysis, so we vary the number of antennas users. This is not done as far as I know in the literature, because the problem is we need to set feasible SNR targets. Usually they are set manually for a couple of SNR targets, representative SNR targets, or maybe for 10 selectively as again representative. But what we did is we automatically assigned SNR targets for each case, because what we did is randomly generated transmit relay beamforming vectors, and we get some SNRs, and from these SNRs we averaged, which in the end they're always feasible, because even after the optimization we can get the same transmit beamforming vectors, so maybe there won't be any power consumption, but the SNR targets will be feasible. Numerical results tells us this, and in terms of this intuition, why we have always feasible SNR targets can be understood. So because of this flexibility, we could do cross-parameter analysis. Here, K is number of users, transmit and receiver, M number of antennas at the transmit and receivers, N is the number of antennas at the relays, and R is the number of antennas, number of relay nodes. So here, it's been a while. So here, the main idea is if we increase the resources in this work, in the first work we are just optimizing the transmit side. M is important. So when M increases, number of antennas increases, we see that total power consumption is reduced, because it is the optimization side. So if we give more resources, it will be better in terms of total power consumption. But some SNR is still increased. I need to remember.
Nice.
So this is the main concept. Actually, if we give more resources to optimization side, for example, here relay number of relays is increasing, but we still have similar total power consumption, because we are comparatively increasing the number of antennas at the transmitter too. So it is richer in terms of optimization variables. Although more power consumption should be spent, we can minimize this, and we can still benefit from the incrementation of relays. So our sum SNR increases. So this is the main idea of these results. And we have iteration numbers as SNR increases, iteration number increase. But we see that this is a comparison to another conventional distributed algorithm. They have more constraints due to different way of writing the SNR. We need to linearize the SNR. They are linearizing differently. They have more constraints. So therefore their iteration number is higher than ours. We are proposing that that's another contribution.
Yeah, that's interesting.
So this is the last work. I will just show this one, the fully distributed version. Use are for easiness of understanding transmit beamforming vectors. This is, let's say, relay beamforming vectors. These are the copied ones at the transmitter side, and at the relay side, these are the copied transmit filters. So in the end, we have 4 sub problems, but 2 general frameworks is enough because they are symmetric. So one general framework is conventional ADMM, the other one is consensus ADMM. To solve consensus ADMM, the solution is significantly different than conventional, because in consensus ADMM we had to write a 2-layered Lagrangian. We obtained one Lagrangian, and then we had to plug that Lagrangian in another Lagrangian. We were lucky to have still trackable results. So we also think this is another contribution of the loss. Since the codes are very intense in the fully distributed case, because we need to copy everything everywhere. In the last work, we didn't do cross-parameter analysis, just showed the main results. So this is the summary.